All right, we are ready to start. So, couple of things. I have uploaded this and my notes. So every on under modules, every week you're going to see not only the modules that I'm writing that covers everything that we covered in this class, but also you're going to see what I'm covering in the lectures. All right. Sometimes they're different. I don't necessarily try to transfer everything to the modules, but may not necessarily be all of the examples that we do. So I also upload those. And then what I'm trying to do right now is to upload extra problems. Whatever I find that I have to my possession, in my possession rather, I will upload those as well for those who want to do some extra, all right, work. Because that's what I hear from some of the students that they would prefer to see some extra examples. All of these, whatever I put up has solutions, obviously. I'm not gonna just give you problems without solutions, all right? Okay, any questions? I appreciate the students who connected with me. That was very helpful because obviously I get feedback from you as well of what it is that I need to do to help. And so that's what I want to say. I need to see a few more students, but we are in good shape. Yes. Tomorrow. Yeah, look at the ending date. Sure. You want me to go over the questions? Okay. Is it okay with everybody else? All right. Or do you want? Okay. All right. Good. I'm just asking. All right. So let me find the quiz here. We'll go to here. Howdy, Canvas. Quiz. Okay. All right. So I will do a preview. The preview does not show the solutions, all right? Preview. It's gonna ask me to enter solutions, but I'm not gonna enter. So here it says, it's one question at a time, but okay, it says conductor one. Is there anything question about this? You want me to clarify?
Yeah, I was kind of confused what the area of
Okay. So it says, let me see what I say. I may have not been clear at all. Okay, conductor one. Okay, so practically, if I were to draw this, I would have drawn it. Okay, let me see. If I were to draw this, and in fact, I have it in one of the notes here. Okay, then I can draw here. All right, so, and I have the solution, so I don't want to see it. Here, I would draw it like, let's put a different color, like this. And practically the material stops here. See? Okay. So with that in mind, let me go to this one and see whether I explain well. What I'm trying to say here, since I did not have the 3D at that point, I say, first of all, it's connected to this voltage, this is ground. This one is electric and voltage, right? Separated from 1 by this, from 2 by this. Conductor 3 is grounded, 3, and separated from conductor 2 by this. Both the electrics extend along the full longitudinal. Longitudinal is along the length. So that's what I wanted to explain here with the other one. I wanted to explain that if this is the longitudinal, the way we see it, they extend all the way until the end, and then halfway here. All right. So, in a way, so this area is 100. I mean, the drawing, of course, is not exactly, but if they extend all the way here and here, up until this area here is half of the total. That's what I mean. All right.
The area of the-
This area of the discovered by the material is half of the total, but the material extends all this way. So by this being half of the total and by knowing this, you can find that one. Well, I did that because I had studied it this way and then I realized with them, but it's an easy problem, right? You guys got, yes.
I was getting numbers greater than what the answers were. I was getting around 2 nanofards. I think my math's wrong or more.
So this area, in reality, okay, this area is half of this area. Okay,
the plates are the same size.
what is it?
The plates are the same size, but the area of the dielectric is half. Like I would think,
So you worry about this?
no, the beginning of the very first one, it says that the plates are all
Yeah,
10
okay.
by 10.
Mhm, yeah.
But then it says that the area of the top one is 100, the area
Yeah,
of the bottom.
because the dielectric one is offset. The overlapping areas is 50, it's half of the area of the total.
Solve it separately for the portion of this passage that aren't built with dielectric. Half that is
So you worry about this?
to the left.
Yes, of course.
The answer once from plate 1 to 3 would be the combined.
Yeah, excuse me again?
The capacitance from plate 1, the top one, to plate 3, the bottom one. That means that once the combined with the half of it that doesn't have a plate in it, combined to a series combination of total.
So what am I asking you? Find the capacitance between conductors 1 and 3. Yes? So what is your question then? Again, I mean,
Does it want just the left half part, or does it want the entire total capacitance?
well, you guys could, I mean, think of the question. Let's think about it. When I have two conductors and I ask you for the capacitance between two conductors, between the plates of a capacitor, what do you think? I mean, what do you mean it's this part or this part?
So the part that has the metal in between it won't just be identical to the side that doesn't.
I don't care. I want the capacitance. I am a designer. And this was an artifact of my fabrication. When I ask for the capacitance, I want to know if I connected a circuit between A and B, what capacitance am I going to see? That's all that I care about. I don't care about anything else. That's your problem. My problem is I want you to tell me what capacitance, if I put a wire here, a ground here, and another wire here, and I want to take the capacitance in this structure, what am I going to see? We solved this problem. We solved this problem in theory. You want me to show it to you? Next what?
Yes.
Okay. I'm gonna show it to you. All right. First of all, this. What did I say here about that? You remember what we found about this? What did we find? What did I say in class? Let's remember. I'm not asking you that. Sometimes I get that style. I do it with my kids when they were kids and they were getting so angry because I thought I was like, so I'm not doing that. I just, so let's think about it. With my different attitude. All right, so what did we find here? We found here something very important. What? That worked as if I had a metal at the interface. Remember I said that? If in that problem here, I have put a metal in the interface, a floating metal, then the capacitance, the total capacitance will have been a series connection between two capacitors and is identical with this one that does not have the floating metal. That's where we said, all right? So keep that in mind. So if I had a metal here floating, it would give me exactly the same result. Then we went down to where? To this one. Well, this one I did not, of course, if I have a metal here, I'm gonna shorten the two and that whole thing is done. So of course, I'm not gonna. This one is two parallel capacitors. So when I put a wire here and a wire there, I'm not seeing this one separately. I see one thing. All right, what happens in here, when I'm out here, this is a distributed picture. And when I come here with two wires, then we're talking about circuits. And when I come here with two wires and I say, tell me the capacitance of this structure that now you have fabricated for me. I want to see one C, one capacitance here. Therefore, what happens in here, it has to be reflected in the value of this capacitance. So that's second. Third, here. Now I'm telling you, I'm solving the problem. But I'm telling you that this problem is identical with what I gave you. Is it not?
Solution doing it that way.
The solution does not go that way. Okay. I will solve it here, but then I'm not gonna grade. How will if I solve it? You don't solve it. No. Who found the correct solution? Does anybody enter the solution that is correct? Okay, you try it. You have a correct solution. Okay. Well, you know why I'm asking. Because I'm a human being. A lot of times I make mistakes too. This one I solved it twice. Now, if both times I made a mistake, what can I say? It is possible, all right? My brain does not have CMOS in there. My brain has only chemical. And depending on what I'm eating in the morning and how I've slept the night before, it may not work well. So I take it, you know, it's happening. It's happened multiple times. Sometimes I have an error in front of me and my brain skips it. So, but if anybody has found it correctly, I have done it twice. Now, if both times I made a mistake, what can I say?
I got the right answer, but the way that I did it, I don't think it's correct.
How did you do it?
So I solved for the capacitance that well, with no dielectric between it, solved the capacitance using the area two plates, and then I added that to the series combination of the capacitors.
Yes. And that's the correct answer.
And I had to divide that by 2 to get the right answer because that is the wrong answer. Which is what I did the first time.
You had to divide it. Are you sure you used the right area? The math would prove that. You had to divide by 2. Now you make me go to my solution.
Well, then
Okay, I can solve this now No? What?
I'd rather get the point.
Okay, I swear to God, I'm afraid now that I may have made a mistake or something, now that you say that. What if I have made a mistake?
Longest mistake, then it's just divide by two. So if you do it the first time, you get it wrong, divide by two.
Ah, okay, fine. Okay, I'm good with, I'm good with that, because if everybody does the same, then I made a mistake and I take the blame.
Multiple choice on whether-
Was that
It's also the fact that it's multiple choice on whether it's-
not unlimited too?
I thought I saw it say.
You say unlimited, and I'm not gonna change it. Did I do it unlimited or two? Okay, well, listen to this. I'm kind of nuts at these days because first of all, I made it one, and then they asked me to correct it. I thought I did two, but I have so many things on my plate, so I'm doing multiple things at the same time. So I think I corrected it, and then whatever, I left it. That's okay. Multiple is good, but try to do it correctly. It's what can I say? Then I have an idea. So we avoid all of this. What if, okay, see, here's my idea. But I will need takers for this. What if I put the problems together, the quiz, and then one person is willing to do the solution for them. I will give this person extra points. And then I will have a solution which I will check.
Sounds like what I did all through middle school for my mom.
Math teacher, yes,
I did all of her tests for her.
oh, good. It's a good practice. So I mean, seriously, because a lot of that, I have to tell you what is the problem. Usually the graders then, or the TAs for a class like that would be in the field, and then I will do my solutions quickly, and then they will go and check them. Unfortunately, the way so far we've been doing it, the two graders, I have no idea on how to check my solutions. So I give them the solutions, I check them multiple times, and then they grade. All right, so I cannot rely on that. So that I can do. If anybody raises a hand and they say, I'm willing to solve this, the person is gonna get. For failing, no, because you're gonna give me the answer and I will correct it myself. And then I will ask around for people who are willing to do that. Okay, you will take the next one. Or this one is done, but the next one, next quiz, all right? Do you wanna do that? Or you want it for this? No, the next quiz. In the next quiz, I will do it ahead of time, and one person, I'm gonna ask for takers to help me with the solution ahead of time, assuming that you're not gonna tell anybody else. And then anyways, it sounds complex, I will explain. I need to think about it too. Yes, yes, true. Okay, well, I will check it again, and since I did multiples, I will let you know if I made a mistake. Okay, let's go to this. Well, now I forgot where we are. Now we are introduction to magnetostatics. Okay. Any other questions before we leave that? Yes.
For the capacitance with the dielectric stands for, do you also multiply it by probability free space?
Of course. Always. So it's always, sometimes you don't give it because it's obvious. All right, but it's always epsilon naught.
So the epsilon times epsilon r.
Yes, always. So epsilon r for free space is 1. All right. All right. So now what we would like to do is to introduce the fundamental equations for magnetostatics, and then hopefully we'll solve a problem today. And then remember also, yes, another question, yes. Epsilon sub r is 1 for, which is the relative dielectric, also for free space.
And then that's also multiplied by 8.5 times the negative.
Yes,
Okay, okay.
yes. Always epsilon, I will write it here, is epsilon sub r, epsilon sub naught, always. Epsilon sub r for the free space is 1, free space. That's why we always give epsilon sub naught for free space. And then for every other dielectric, we don't give the whole thing, we give epsilon sub r. All right? Okay. Now, okay, magnetostatics. Remember, we started, everything starts with a force. So the full force, the electromagnetic force is electrostatic force plus magnetostatic force, all right? And what we found for electrostatics, that is equal to QE. For magnetostatics, that you have that if the charge moves and then is cross product with a magnetic field. Both equations involve two types of sources. On the left, this equation involves Q and another Q that produces that E. All right, so in reality, there are two Qs in there. And in this one, in magnetostatics, you have one Q that moves, which is a current, and another current that creates that B. So you remember that. Don't think that this E is due to this Q or this B is due to this current. So in fact, I can rewrite this one to be I cross B, where I is nothing else but Q, and of course that, right, QV. And why I has a bar? Because it has a direction. Always the current has a direction. So we have these two. And in fact, here also, we have this and that. Then we have that we have introduced the electric flux density dE. And this is equal to epsilon E. And in fact, I don't even have to put this one because it's different. So this is the electric flux density. This is force. And this is, I will not, since you know it, I will leave it like that so you can see. Otherwise it's going to be full of writing. Okay, so here. Now, in magnetostatics, we have the magnetic flux density, which is B, and it's mu H. So E for H, D for B. All right, so practically I can lower this down to see a little bit the duality. So you remember it like this. So this is all right, this is here, this is here. And I have, of course, in terms, this is electrostatics. Okay, I don't know where this came from. Ah, there. All right. And then this is electrostatics here. So I want you to remember at least this, the duality. All right. So the magnetic flux density, B. The electric flux density, all right? So here, electric flux density. And here, magnetic flux density. Okay. Now, we have here Coulomb's law in electrostatics, Coulomb's law. That says that E equals 1/4 pi epsilon. And then you have, let me see how I'm gonna do that. This Q R, no, this one. I will do it. Let me do it like this. Over R cube. Remember that? This is the R, the electric field that is produced by a charge, and let's assume that the charge is a volume charge in the most general sense, all right? In the most general sense, charges will be in a volume. In that case, where this is the volume of the charge, this is called the Coulomb's law. Okay, so in magnetostatics, we have the Biot-Savart law, which says, and here, that the magnetic field H, and I need to remember the constant, is I/4 pi is 1/4 pi, and then is the surface. Now current I cross, and then this is a current that is a surface current cross R over R cube. So now you see that, and instead of Q, I have current, where the current is what a moving charge creates, but it's a current, all right? So we are gonna, in magnetostatics, we are moving away from talking about charges to talking about currents. Even in reality, those are charges that move. Okay, so Gauss's law in electrostatics. What does it say? Divergence of D equals what? In the most general case, always, Gauss's law is a differential law. It applies at one point in space, one. At that point in space, the divergence of the electric flux density is equal to the charge at that point in space. All right, so that is Gauss's law. So here we have the, let me see, it's here, Ampere's law, which in fact I'm gonna write it. And we are not gonna spend too much time on this, but so you remember it, and you have seen amperes, all right? Amps is what we use for the current. Ampere's law says that the curl, so let me see, Ampere's law. Says that the curl of the magnetic field intensity is equal to the current. I should probably, okay, that's okay. I'll do the current by I. At one point in space. Now this current at that one point in space is gonna be a density, all right, current density. So this is charge density, so we can remember those. This is volume charge density because it's in one point in space. Density. And how do we measure volume charge density? In Coulomb's pair. All right. Now, let's go to the dual thing, which is Ampere's law. only also at one point in space, and says the magnetic field, magnetostatics here, the curl of the magnetic field at that point in space is equal to the current density. But what current density would that be? If so, we remember a little bit what we discussed last time. Cannot be a volume current density. No, because the current, what is it? It is a charge that is moving along a particular path. And that moving charge along this particular path makes the current. So we cannot have volume current density. We have surface current density. And in this particular case, this in the most general case is going to be a surface current density. And what are the units? Amps per what? Per meter squared. Okay. Now, what else should we say? A divergence theorem. So you see now the duality in all of this. Let's try to go one step further. And then we'll start solving problems using just that. So here, divergence theorem, divergence theorem. You remember what the divergence theorem said? It said that if I take the volume integral of the divergence of D, which in fact makes the volume integral of this charge density, which is going to make Q, all right, is whatever Q is in that volume, not outside of that volume, in that volume, as we have seen. In that case, that changes, according to the divergence theorem, to a closed surface integral of D dot ds on this surface, and that is equal to Q. That is enclosed within that volume, right? Or enclosed by the surface. Now, what is the dual of that? Stokes' theorem. What does Stokes' theorem say? If I were to take Ampere's law and integrate it, and since my current is a surface current, I will have only to integrate it over a surface, all right? Because the current comes like that, only over a surface. So the Stokes' theorem says, if I take Ampere's law and integrate that over a surface S, and of course, if the current flows, like assume, that is the current that flows here. You remember I told you that something like this has multiple currents that are separated. So if I wanted to find the current that goes through an HDMI cable, then practically it's only the density on, if I were to cut the cable here, there's not going to be current, but the density of the current would have been a surface current density. Because in fact, if I take the cross section, if I knew if the current density is uniform on this cross section, I take the cross section and I multiply the surface current density with the cross section, I know how much is the total current here. All right, so practically what that means is the following. If I were, so let's assume that this is an HDMI cable. Okay. And then here there is current that is flowing. And then it comes like this. All right. Through, and then this is the outside the plastic. And then the current flows in that direction. And each one of these lines is a density current. All right. So the current density, it will be here a function of the position on this cross section. So it's going to be, let's say if this cross section is rho and phi, it will be a function of rho and phi. That's what we are using for circles, all right? Rho and phi, polar coordinates. Then to find the total current, which we normally show with capital I. Capital I shows the total current. So the total current, we will have to integrate on this surface, all right, of this cross section. So practically, if I were, therefore, to erase that and do it nicer, let's assume now that I have the cross section of this HDMI cable. And on this one, I have practically here currents that are flowing like this. All right. And to be able to find the total current that flows, let's assume that it's like individual little cables, all right? To find the total current that flows, I would have to integrate. All right, so if this here, if this one here is a current density and assume that is uniform, and therefore is rho phi, because that are the polar coordinates that we use on a circle, then the total current that flows through the surface is nothing else but the integral on this circle of the current density. Okay, what does Stokes' theorem say? That this is, so the surface integral of the curl of H, which is the surface integral, therefore, of this I current density. All right. And in the surface integral, since, let me move this a little bit closer to this end. And then here, have this one to be accurate mathematically, because surfaces have a direction. All right. You remember we said that. Then Stokes' theorem says that this is equivalent to a closed line integral of H dot dl, which gives the total current. That's Stokes' theorem. We use Stokes' theorem the way we used Gauss's theorem. All right, same way. Now, what is the relationship between these surfaces? Let's assume that this is my surface S. Here. What is the relationship between this surface S and this path line C, which is a closed path? This is S. What is C? Let me see. C, it's this one. Okay, and so C is this. And what is the direction of C? The direction of C is this one. Assuming that the current flows like this, so it comes out of the board, as we have agreed on the, how do we indicate that? Assuming that the current comes like this, this is the direction of C. C. And we call that also the right-hand rule. Current like that, out of the board, C like this, okay? So these are the most critical equations that you will see between the electric and magnetic fields. All right, so I want you to remember those, because practically we are going to use mostly these instead the equivalent of this, so that. So practically Ampere's law with Stokes' theorem, the same way we use Gauss's law with divergence theorem. And now we are going to solve some problems, all right? So you can see how to apply that. Okay. All of this is there. I will clean it up, but I have it, my notes. So now, problem number 1. we have, we start with something interesting here. First of all, assume that we have an infinite wire, all right? The simplest problem you can solve. Yes. Oh, I'm sorry. I did not see you. Thank you.
So is C the current or your closed loop?
C is a closed loop here. The current is here. I'll make it a little thicker. No, in fact, I will do it here. But it's, yeah. Okay. This is the current. All right. Okay, so the easiest problem we can solve is this one. All right, so what do we do? Same thing. We start with we know our field here. First of all, we assume it's infinite long because the current has to close someplace. The current and the magnetic field lines go on closed paths. All right, always. It's not like the charges and the electric field lines where charges can be finite. The charge can stand on its own in some place. And the electric field lines go from one charge to another charge and stop. In magnetostatics, the currents close their lines and the magnetic field closes its lines, but they're perpendicular. Okay, so here, for example, we have a current that goes to infinity, which means it's a part of a huge circle. I mean, assume that the circle had a radius of 100 meters. What we see here is almost straight. That's what it means, all right? So, question number one, what kind of magnetic field are you gonna have? How is the magnetic field gonna go? The direction of the magnetic field. The direction of the magnetic field is gonna be like that, the red, you see? The magnetic field is gonna go like this. And if you go a little higher, it would be more lines, all right? So it will be, the magnetic field is gonna always look like that. Let me use, it's gonna be like this, and like this, and like this, all right? And so what we do out of all of this possible, what do these lines mean? It's like equivalent to equipotential lines, to remember, but we don't say that. We don't have potential for magnetostatics. But we call that the lines of the magnetic field. It means that on each one, on this line, on this circle, all of them are circles like the red one. Every point on this circle, the magnetic field has the same path. And it goes around like that, all right? The same thing happens in this circle. The magnetic field everywhere on this circle has the same value, and the same thing here. Okay. So then out of these circles, we select the red one. And then we write for that. Now, why do we say that everywhere here has the same value? First question. How do we know that everywhere here on this circle, the magnetic field has the same value? From where? From Biot-Savart. What does that say? That the only, all right, so you have a current, and the current is like on the axis of a cylindrical coordinate system. The magnetic field at every point where it has the same R, from the same distance from the axis of the cylinder is the same. So that's this one. This one just told us the story. All right, we don't need to go anywhere else. So they say, according to Biot-Savart law, from any section of a wire that creates a magnetic field at any distance, the same distance from this wire or from this current, I have the same magnetic field. And it varies in reality because of this is looking as a cube, but in reality it varies as what? 1/r squared. You remember that? R squared. And why here I have R? Because that's how we use it most of the time. But if I were, I would write it next to it, as a matter of fact, so we never forget that. Let me write it next to it, that this one is equivalent. This one is equivalent to, okay, let me write it separately. No, I will write it the same. Is equivalent to 1/4 pi. Same thing here as I cross A sub r, which is the unit vector, divided by magnitude of R squared. Okay, so you don't think, so you remember the square too, because I showed you that, but I talk about square. Don't talk about cube, because the cube here with this one cancels out and gives a square only. All right, so we remember that. Okay, so now I'm going to this problem and say, okay, now let me take, now that I know that it's all of the same, I take this, it's called path C. I know because that my magnetic field goes like that. So now I go to Stokes' theorem. All right, first of all, I start with Ampere's law. All right, go to Stokes' theorem. In fact, I take Ampere's law and I said, okay, this is all my current. This is it. So what I will do is I will take this area, whatever the area of the circle, and if I cut the area of the circle, or if I integrate over the area of the circle, the total current I'm going to have is going to be I. Do you agree? Okay. So I'm taking this, I integrate both sides of this over the area of the circle that has also this direction. And then I get I here, all right, because it's anyways, this goes through a line. So it gives me I. And then here, I use Stokes' theorem for that part. And therefore, it goes from here to then here, which is the closed integral of H, which is constant along this circle, along that circle. So I have a constant, and then the integral of this constant along the circle. So it's constant times the circumference, all right? And therefore, it gives me exactly what you see here, the constant, which is the value of the magnetic field on this C circle times 2 pi, and D is like the radius in this particular case. So what I found, and here there is a small numerical example. I found that if I had a current which flows on a filament is the line, all right, very thin, then the magnetic field from that is always changing as 1 over the distance. Where in electrostatics we have seen 1 over the distance change? What kind of charge? Line charge. So see the similarities. For a line charge, the electric field varies as 1 over r. For a current, which is in fact is like a line charge that is moving, the magnetic field is changing as 1 over the distance. So you have these two similarities. So look at this problem and look at the what we have done here. And from there, we're going to go to more examples below that, which is then a current that flows in a loop. And then we'll see 2 loops, and then we'll see other things. All right. So And we are gonna end, why do I stay with loops? Because from loops, we create inductors. So that's how we are gonna go in magnetostatics. All right? Thank you. Yes.
This is what I was saying. I was getting 2 picofarads. But what am I doing wrong setting up here? Treating C1 as the side without the dielectric in the
So
middle.
let me see. Let me see since you're here. Oh, no, I had it here somewhere. So boundary conditions. Okay.
Mhm. So I got the capacitance across this one's going to be 1 times 8.85, 10, 12, 50 millimeters squared, which is 50 times 10 to the negative 6.
How much did I give you for D? give you-
1 millimeter.
For each one of those?
Yes, ma'am.
Yeah, yeah. Okay, so this is
I'm
2.
assuming the conductor here is infinitely thin.
Yeah.
Okay.
So this is 1/2D, this side,
Yes.
okay? And then you have to get the series combination of these two,
Yes.
which in fact is this. The series combination of the two is 1/this, 1/that. So C1 times C times C. The series combination of 1/C.
They all make them look the same.
Okay, so 1/C equals 1/C1 plus 1/C1. These are the same,
For that's you're just solving for this
Yes.
slice. Okay.
which is gonna be 2C1 over C1 squared.
Okay. Yes.
I put the 2C1 over C1 squared. Okay, perfect. Now I'm correct. And then C therefore is gonna be C1 squared over 2C1. And therefore it's gonna be C1/2.
Uh-huh.
You got that?
Trying to think through.
Okay, C1/2 is 1/2.
okay.
C1/2, the 2 there, and then it's half of the area, 1/2 epsilon r over d.
Is it you're solving C1 here or
This is this. 1/4 epsilon r a over d.
question? The equation for just one of these.
Mhm. The equation for just one of these is area A prime
Uh-huh.
epsilon
Epsilon.
divided by d.
Okay, so I'm not doing the series combination. That's what I'm not doing. I'm treating it like an
Yes.
electric field.
Oh, no, yeah.
Okay.
See?
So it's all
Yeah.
the series combination. Okay.
Yes.
Thank you. Thank you.
Okay,
I was just curious for the individual, so we're doing test corrections.
yes.
Like, what exactly are you looking for?
So I want a new solution of the homework because I gave you some slightly different, all right?
Oh, it's okay. It's a little different.
It's a little different. So
What?
solve it,
For the individual?
which for the individual, yes, for the individual. We are talking about the individual or the team.
Yeah, the team, it looked the same, but it's like a little bit different. The individual, I thought it just said like do your midterm again.
Maybe I did. I don't. I give all of these problems. So the individual, I don't give you a different one.
Yeah, I
It's
think
the
I
same.
think you just
Solve it. Now that you know how we solve it, you solve it like you solve it for the first time.
Okay.
You would solve it like as if you were here, knowing how to do it.
So if I got 250 on the first time, do I
You will
just kind
solve
of do
it
it again?
because yes,
Okay.
because the 250 you got was very generous.
No, I knew it was.
So if you
I saw that, I
don't
was
do
like,
this again, you're gonna force me to go back and grade it.
Okay, that's what I was. That's
You
why
don't
I
wanna
came
do
and
that.
asked. Yeah,
You
yeah, yeah.
don't wanna do that.
Okay, and do I turn in like the midterm and then the corrections, or just the corrections?
And the midterm at the back.
Okay, so like both.
Yes. The way it was the midterm, not corrections. I mean, the old midterm, I have it, but I want you to attach it so I don't have to go back crazy. you know,
Okay.
into
I think I
databases.
understand. Okay.
You understand?
Just wanna make sure.
All
Okay,
right.
thank you very much.
Sure. Hi.
Wednesday, Sean.
Yes, yes, Sean.
I did work out the problem. I did
Yes.
the series and the parallel, both of them.
Yes.
Just come out. You have to do a one half problem.
Yes, yes.
Just double checking with you because it threw me. I had to solve it backwards.
So this is the problem, or this is the.
This is working backwards from 0.55.
So this is the quiz.
This is no, this is something else. Don't look at that.
Okay, well, this is the quiz. Yes, this is the quiz. Okay, so here, yes. So, okay, let me see. The 1/2 comes from the combination of the series combination. And then there is another 1/2 because the area is public.
Okay, so that I did the 1 and 2. This is the series right here. I got
Yes,
that divided by 4 dot.
yes, because of that.
Okay.
Yeah, one
And
by
this was
one.
just because we're doing half of it. Oh, okay.
Yeah,
That threw me. That's it. Thank
okay.
you very much, man.
Mhm.
So for the exam corrections, I use this E equation, right?
Yeah, Q/8, where's Q here? Q/8.
And it's because it's a plate at distance
Because,
doesn't matter.
because, yes, yeah, a bit down here.
Right? And
Yeah.
then for the other
See,
part,
this is all of Q,
so it'd be not divided by 2.
no, because every line from Q is gonna terminate here.
So it's same thing, but
Same
not.
thing, yes.
Right, and then the quiz one, I just, I mean, I basically use this equation.
Yes. So you said just have, yes, so that gives you 1/2 because of the combination. And then you get another 1/2 from A because it's half.
Wait, another 1/2 for me?
A1 is half of A2. Not here, I mean, in the problem that I gave you this, it's half of the other one.
But, so in this example,
Yes.
translate,
Yes.
A2 is its own thing.
Yes,
I got like around
this,
0.22.
so this is this is in parallel with the combination
So
of
they
these
just add.
two. Yes. Not that, no, they don't add, these two
Those
are,
are in
yes.
series, those
Yeah,
add,
yes,
yes.
yes.
So then those, since they end up having the same area and
Yes.
they have the same distance.
So the
between each
total
other.
is half of the one.
Okay.
The
Yeah, that,
total is half of the one.
yeah, that's the thing, I might have to work it again.
Okay.
Have class.
Alright. Okay, but you are on the right path.
Thank you.
Sure.
We were wondering about for the team assignment. It's pretty similar to like what we've seen before, but instead of like a point chart, it's like a
Yes.
container chart.
Yes,
So I was like wondering like how that would like change the problem.
so it's going, instead of having a total Q, so the chart still splits between the upper plane and the lower. And instead of having a total Q, you have a charge density.
And how did we find the charge density?
I gave it.
Oh, you gave it to us?
Did I give it or I said that? Yes, I gave it to you.
Okay.
Otherwise, if I give you a charge density, if I do a density, I have to give it to you.
So the only difference is pretty much the units of that.
Yes, and then the physics of the problem there too.
Thank you.
Sure.
Also, one quick one, would this be acceptable work? Just going in and playing with the value
Sure, yes.
or turning it in? Thank you.
Sure.
I don't know how, like, I feel bad, I'm not trying to like ask you for the answer, but I just like want to know, like, it's like a lot of because like, I know like this is like the equation for like an electric field,
But this is out of one charge. Here you have a charge density.
but I use this equation like charge density.
Okay, fine. Yeah, but you don't have the Q, you have the charge density. What did I give you? Yeah. What
Yeah,
did-
you give me
That's charge density. The charge density. Look at the units.
But in your solution, didn't you say like Q sub S equals Q over 2 like
This, right?
so yeah,
yeah, I guess like how is that different?
yeah, let's just do that.
Right? Is
Yeah.
Is that
Because
Wait,
you
no, I
said
thought
you
it's
do it,
Q
but you
over
don't
2 on
know.
this one. Yeah,
Yeah,
hold
I
on.
think
Q sub S equals Q over.
I tried to solve for Q.
Yeah, I think it's Q sub S equals Q over 2.
Where did you find that?
Q is equal to Q sub S.
Where is this? Oh, from this
Q
one.
S is equal to Q
Well,
over.
you
Oh,
don't
I
know.
was from.
Work with charge
Yeah, but
density.
then that's when you put that in there. It's like Q.
All right, you don't need to go to Q.
It's
Just
Q
work
over
with charge density.
That's the actual equation.
I guess like I'm confused.
In the
What?
Oh, is it just this over this?
Yes.
Oh, okay. 'Cause theoretically, wouldn't it have still worked though?
Yes, but you know, it's very possible to make more mistakes here instead of
I
just
got like
those.
some
Wait, so
weird
what's your question,
vowel,
Deepa?
you know,
I see
but
what you're
like,
saying.
Nano is okay,
So,
but I don't know because it's over. I don't know. Nano is, I will not worry about that, but you going through this, you don't know how much of a mistake you can make. You know, why not going from this?
but would it still be like divided by 2?
Yes, that is correct.
And then like, sorry for
I have to go to my other class, I'm sorry, but yeah, please show me quickly.
like for this one up here, is it just one? Is it just one plate, or is it?
Where do I ask them down here or here? Pero I am, I'm asking
You're asking
myself.
for the.
It's the same like the
So if
previous.
we're already given that, then what do we even?
There's no sense, there's nothing going on.
So then what's our question?
Because where is the?
Like if we already have then it's asking for the electric field, right? Oh wait.
No.
No, do we even need to because the Q sub S already includes that?
No, if they see the electrons, do you think they're gonna go someplace else?
Wait.
I mean, it's like I have myself hanging over the earth and you say I'm gonna go up. I cannot go up.
Of the planar charge.
Get out.
It was a planar charge.
Now, if there was another earth on the other side that would stabilize the middle, because it would be one force on one planet.
Is
the
it
other
A or
force on
2A?
the
Is that what-
planet in the middle.
But why does that matter? Because like we're still gonna be like finding the direction
So
and
would there still be
find the magnitude of the electric field, right? If we're just finding the magnitude of the electric field, it's just Q sub S.
Thank you.
Yeah, I didn't overcomplicate it. It should just be like. Doing you guys? Yeah. Yeah. Yeah, dude. You can erase it.